So for those at home or who potentially showed up late, that is the first page of the exam. So you've got a partial periodic table, you've got the functional groups listed there, and then we have that naming of functional groups box, which I think that naming of functional groups box is going to disappear by the next exam, for the record. And I think the functional groups will also disappear by next exam. So those bottom two things are going to get pulled for exam 2, but they are on the first page for exam 1. Okay? Let's quit that. Don't save. Hopefully I don't regret doing that. So some exam 1 notes. So a couple things. One, based off of this, you might be like, it doesn't sound like it's written. That's because it's not. I'm not finished writing it. So a lot of that has to do with just the fact that my wife was out of town, and so I've had the kids all week, and it makes it harder to get anything done. So I got the vast majority of it done yesterday during nap time, and was happy enough with where I made it to that I think I can finish it today without too much problem. So yeah, currently what I've got is I took 5 to 7 questions from an old exam / kind of information from the slides a little bit. Yeah, you don't have access to that old exam. Sorry. It's an exam. And then I went through and started with the practice questions, like the suggested multiple choice questions. Everybody know what I'm talking about? Does head shake yes?
From the, what we pull our homework from?
Yeah, not the textbook, but that linked document. That face says no, so let's make sure you know what we're talking about. It's got something like 80-something questions, I think, in it. Oh. Or it actually, I think the number says 80. I don't know if there's actually 80 questions.
I didn't realize that was different, sorry.
Well, it just depends what exactly you think I'm talking about versus what I'm talking about. Well, so let's make sure we're on the same page.
The doc.
The doc, yes.
Yeah, I didn't. I thought it was just a list of the same questions from the homework. Or from
No. The doc is questions pulled from we'll call it a secret test bank, for lack of a better description. And so those were all questions from that bank that I thought were reasonable to include, so I included them. Or included them as questions for you to practice, and then, what did I say, 17 of those questions? 14 of those questions made it more or less directly into the exam. In some situations I modified the question a little bit, so they aren't exactly perfect. For instance, on how it does images isn't the nicest, and I discovered per Annie that sometimes it didn't actually put together the questions right, that it didn't print symbols correctly. So there's a couple questions that it should be showing a positive charge and it just shows a circle, or it shows a vertical line instead of the actual plus of the positive charge. So I had to go through and fix those kind of things. And then the rest of those questions are either coming from just stuff that I think we've talked about throughout these first 4 or 5 weeks, or directly looking at the slides is usually where I start and be like, that's what I talked about, let's ask some questions on that concept. Okay. Oh, and the first thing, if you open up in the modules, there's, for this week, the exam 1, it lists a whole bunch of topics and numbers next to them. Those numbers are ballpark with the questions, how many questions are per those topics. Kind of makes sense? Questions about any of that? Okay.
Sorry, 50 questions?
No. I'm going to say at most 40, I think I'm hovering closer, yeah, I think about 40. Right now, I've got 35 points of short answer. I think that's right. And I usually like to I'd like to float closer to 80 points for the multiple choice, but that means 45-ish questions. That's a little high. So it'll probably be something like 75 points worth of multiple choice. And if you're good at math, you'll realize that goes over 100. That excess over 100 just won't count towards your grade. So we'll call it 110 points possible, and you get graded out of 100. So 10 points are almost,
Cushion?
yeah, cushion is a better way of phrasing. Okay? Kind of, sort of? Just some test taking strategy we'll also cover here real quickly. Where should you start the test?
The hardest ones.
No.
The easiest ones.
Okay. And easiest becomes and both those statements become eye of the beholder. What I would phrase instead is start where you know the answer.
Where you feel more confident.
Where you think you know what's going on, that's where you should start, regardless of where it is in the test, which does mean you need to review the whole test before you actually start going into it. If you start with question number 1, the very first question could be very, very, very hard. Okay, that means you're taxing your brain a lot and you're starting to break down your function. If you go through and find the easiest answers for you, you can guarantee those points fast where your brain function is at its highest. You can then start going through progressively to the harder questions. The harder questions are hard, which means you were likely to get them wrong. Spending more time on them just means you're wasting time. Okay? The spin I usually like to do is if you envision an ER, right, and you have multiple people come in with, let's make something awful, bullet wounds.
Triage.
Right? You have to triage. You have to decide where you can actually save someone versus they're too far gone to actually help. So you have to be able to triage that system. You got to do the exact same thing with an exam. Okay? Ballpark recommendation. It's a slightly shorter exam than my normal exams, but ballpark, it's about 1.5 minutes per question, maybe a little bit more than that. So if you're staring at a question and you don't know what to do, you're wasting time. Move on. Okay? At the end of the test is when you can start worrying about bubbling things in. I'll give you a 5-minute warning. At that 5 minutes, it makes sense to go through and bubble stuff in then. Okay? You can bubble as you go too. Some people find that kind of cathartic. I do, and would bubble things in as I go. Okay? But your first step should be read through the whole exam real quickly. Identify those questions that you think you know well. Answer those questions, and then slowly just start bouncing your way back and forth through the test. As far as materials you're allowed to have, you are allowed to have a model kit. What I would recommend is a cyclohexane, and I guess I'll draw it. So you can take a cyclohexane structure, so a 6-carbon ring. I would put on 2 carbons. To those 2 carbons, I would put a green ball, a red ball, a blue ball, and a white ball, and then I'd leave the other 2 blank, or if I could find another color, maybe a yellow ball, depends on the kit. Okay. That way, you now have a structure that can answer pretty much any question that gets thrown at you. You're concerned about Newman projections, you quickly break the bonds. Okay, you could break, say, this bond and this bond, and then you could move the white ball over to here, you could move the yellow ball over to there, and you've got a Newman projection that you can cite down. Okay, or you've got a Newman projection here that you can cite down. This means when you go through and look at the questions, you would write on the test G for green, R for red next to your individual groups, so that you can then interpret what the question is saying versus what the model shows. It allows a smoother transition for being able to process through it. Theoretically, you've worked with the model so much, you don't need to do this. Okay? But it can be handy to have it there. Model questions I would save for the end because that takes time to build those things out. Okay? If you've got a question about cyclohexanes, which we'll look a little bit more about, you've already got it pre-built and you can now answer questions about cyclohexanes. Okay? If you've got a question about chirality, you break this one bond and you now have a chiral atom that you can evaluate, again, with all your different colors. Kind of, sort of? Okay. Yes?
Is that only if you bought the kit yourself?
I will try to grab, well actually technically I have a couple kits back here, but I only have a couple. So if that's the scenario, you aren't working with a model kit, it's probably not going to help you. Okay. I'll still have them just in case, but it's probably a lost cause to play with a model kit if you haven't been using it already. Okay. Probably, but not a guarantee. Kind of, sort of? Okay. So what do we want to look at now? Unfortunately for Katie, and now she's probably swearing at me while she's watching the video, what we want to look at is what's going on with our chairs. Okay, and the problem with why she's swearing at me is the majority of this is going to be looking at a model kit. Okay, so we want to be able to envision what our drawings are showing. Okay, and so one of the big things that we would want to evaluate first and foremost is that if we were to look at kind of this, what do we see? What do you see right here? Can you give me any words to describe what you see? Right? Staggered, what did you say? Staggered. So we're looking at a Newman projection. Okay? The reason we look at Newman projections is so we can see staggered and eclipse and all that, which is all energy. So anytime you see a question about energy, really what we're asking, what's the Newman projection look like? Because that's the sole reason we go into Newman projections, is to understand something about energy. Okay? So if we're just looking at kind of a standard system, we'd be like, okay, well, a couple people at least saw that was staggered. Does everybody else agree? Do you at least see the staggered? Okay. Well, now what happens when we go up to a ring, cyclohexane, is everybody looks at the structure like this, and they go, I don't understand what you're talking about with a Newman projection. That's because you can see all the bonds of the ring. That's not a Newman projection. When we shift to a Newman projection, you have to hide that bond. So we were looking down that bond, so it disappeared. Okay? So where my left hand is, do you see the Newman projection on that left-hand side? That's your right-hand side?
Sorry.
That's your left?
Oh,
It's
never
your
mind.
right, isn't it? Okay? But hopefully you see the exact same Newman projection. It's right down that same spot. There's technically a second one right next to it, out where my right hand is. That one's harder to visualize right now because I didn't put in all the bonds to show them. Okay, mainly because I ran out of time. But that is kind of the Newman projection of the chair. Well, why do we need such a complicated structure? Okay, and really what we're talking about is that as we move up, actually we'll still do it with the model kit, with rings, is that we'll know eventually sigma bonds can rotate. And if we had a 3-membered ring, I wouldn't be able to do this rotation. Okay, so does everybody see that we're actually rotating a bond? Okay.
Yeah.
And in particular, we're rotating this bond here. Okay, in fact, actually we're rotating all of them as we go, but I'm trying to rotate about that bond. Okay. It's not a full rotation, because a full rotation would say I could spin it all the way through. Okay, and because this model kit is so resilient, I could probably do it without it breaking. But for the most part, that should be really hard to pull off, because you're forcing the model to do something that it doesn't want to do. Okay? But what we're talking about is that simple rotation back and forth. Well, why does that matter? Okay, well, let's look at a potential reason why that matters. Okay, when we're looking at this, where we can see the red and green for our Newman projection, what Newman projection did we say we were looking at? Staggered. What happens if I say I take this and I'm just going to rotate? What is it now? It's eclipsed. Which means when I rotate these atoms, or those sigma bonds, I can move through different energy states. And if I'm moving through different energy states, I have to call attention to that. And just like we did with the staggered and eclipsed, I have to name them differently. Okay? It is still staggered and eclipsed, but they're now referenced to the cyclohexane structure. And what you'll hear often is something known as a chair. Okay? The chair isn't particularly obvious to see. Well, let's see. Here we go. When we're talking about the chair, what we're taking is our structure, instead of looking at it from the top, the overhead view, and instead of looking at it bond on, end on, okay, we look at it kind of from the side. And we're going to look at it from this side. Right? Why is that important? Right? Well, if we sat in this as a chair, and envision it more like a lounge chair, this is where you would put your back in the chair. This is where you would hang out with your, sorry, feet does not begin with an S-O, but I'm so sloppy in writing, I can make that an F. Our feet, and right through here is where we would sit, okay, or our seat. Right? And if we look at this drawing here, my right hand, so your left side, is my back, okay, or what I would typically reference as a head. Okay? Where I'm grabbing with my left hand is now where I put my feet. The remaining 4 atoms of the ring are all in the same plane. Since they're all sitting in the same plane, that would be a nice level space to say, sit down, that's our seat. Okay? That kind of vaguely looks like a chair. Okay? As opposed to, and if we turn this around, maybe that helps to see it without the green and red atoms. Everybody kind of see that chair? If I sat in this chair, where would I be facing? Okay, cool. Okay, you'd be facing to your left. Okay? And here's one of the gnarly things with chairs. If I sat in this chair, where would I be facing? Where would I be facing? Be aiming right over my shoulder. There's the back, there's the seat, there's where you put your feet. Everybody kind of see that? Okay. So an individual ring structure, cyclohexane, technically has 3 chairs, okay, facing different orientations. And all it takes is a subtle twist of your hand or the structure to change where it's sitting. Now if we sat in the chair, where is it facing? Yeah, it's out that direction. Right? So we have to be real careful in kind of acknowledging those different shapes and those different representations. Right? Why do we care about those representations? Well, we already talked about one of these aspects, that if we looked at it bond on, what happens? What Newman projection are we seeing? Staggered. And staggered is low energy. Okay? If I take right now this bottom part that's kind of facing you and I pull this up, now what do we have? We have eclipsed. Okay? So the eclipsed is not a stable configuration. Okay? And since it's not a stable configuration, we probably shouldn't call it a chair. What should we call it? Well, what does it look like to you? Ship can sometimes be vague language. I usually call it a boat. Okay? We've got this kind of boat ship shape. Okay? So you can hear a reference between boats and chairs. Depending on what you decide to look up, you will hear all sorts of other references to there being twists and twist boats and all those other things. All I really care about is boat and chair. Okay? So let's go back to the chair for a second. Right? We're looking at it end on, right? Newman projection. Okay? Why is this going to be important for us? Well, we could draw out a Newman projection to see what it looks like. Okay? So in this particular case, you're now looking down the seat atoms to see your Newman projection. If we're going to add some information on it, what can you tell me about this carbon? What do you mean by backside? Elaborate. I did this unintentionally and it was a mistake. I should have done the other one first.
Again, is here.
Okay. This atom should be in the back of the molecule. Okay. So it's all the way behind everybody. Kind of makes sense? Okay. It's also the back of the chair. Okay. That's where you would sit your back. Does everybody kind of see that? What happens with this atom?
This one, the in front.
We could say it's the one in front. I'm okay with that. But push deeper. It's where you put your feet. Okay. So here we go. Okay, I'm going to try and keep my right hand, okay, on that back atom and my left hand on the feet atom. Everybody kind of see that? Okay, I want to go through what's known as a chair flip, okay, or a ring flip. They're all referencing the same thing, okay, and this is where it gets tricky. What they are not referencing is this. We're looking down, it's okay. This is not a ring flip or a chair flip. Okay? That's just a flip. I flipped the molecule over. Okay? So one way you could envision that is flipping like a pancake. That's not what we're talking about when we're talking about ring flips or chair flips. Okay? What we're talking about is I want to convert this lounge chair, like the really fancy lounge chairs you can like lay out. Okay? So you could lay flat on it and then you could pop up one end and you'd be facing the other direction. This is what we're going to do. We're going to take my place where I would put my back and I want to lie that down. I want to recline it. But as I recline it, that's going to be kind of a high stress system where it's all flat. Okay? That's not exactly eclipsed. It's not exactly staggered. It's a little bit kind of twisted. Okay? This is starting to get into that twist configuration. But I'm going to push all the way down. I'm going to take that back and make it kind of aimed downwards where I could sit in it. Or where I put my feet, sorry. Does that make sense? Now what I'm going to do is take my old place where I put my feet and I'm going to move that up to where I can now put my back. Everybody see that? Where am I sitting in this chair? Where do I face?
That way.
Hopefully you see if I'd be facing me. If we go back the other direction, I'm going to take my old back, my new back, turn it into feet. I'm going to take my old feet, turn it into a back. Now where am I facing? Okay, towards you. So when we go through this ring flip, we're not flipping the molecule over, we're not turning it, we're not rotating it. We're staying in the exact same seat place, except we're changing our head and our feet. Kind of, sort of? Okay. Why do I care? Let's take a look at these green atoms. Where are those green atoms located? This is your left, right. Left.
Left.
It's your left. Okay. So we'll attempt to adjust this. Okay. It's on your left, which means that should be a green atom and that should be a green atom. We good with that? Okay. Describe to me where they are. Where's your focal point when you think about a Newman projection? Where do you start your looking when you think about a Newman projection?
The anti.
Using fancy words, okay? So we gotta be a little bit careful with that, okay? How do you know you have something that is anti?
Opposite.
Opposite what?
Atom.
What atom? If I'm thinking about an anti-Newman projection, they're on opposite sides. Opposite sides of what?
Plane.
The plane. Where's the plane? That's my carbon atoms running right through here. So when we're looking at this, this is our plane running right through the middle, which means those green atoms are on opposite sides. Why is this going to become important? Where are the red atoms? They'd be there and there, right? Aren't they also on opposite sides? Yes. So saying Anti gets a little bit better because it's not just opposite sides. Okay, anti and really far away from each other. Okay, we could push. Does that make sense? Everybody good with it? Okay. What happens when I go through that ring flip? So we take the back, pull that down. Take the front, pull that up.
The ones that you're moving, the back and the feet, are switching sides of the plane?
So I'm going to push on that a little bit because I think I understand what you're saying. We'll color that blue, we'll color this purple. Your blue that was in front and below the plane is now where?
Above the plane?
Above the plane. It's still connected to the front atom, right? What happened to the purple atom?
It's below the plane?
It's now below the plane, still connected to the back atom. Everybody good so far? Okay. What we're looking at is effectively then the, whatever it is, peace symbol or Mercedes symbol. I don't know the shapes. Okay, but kind of inverted with each other. Everybody see that? Okay. One thing we should note, the shape in front here, what letter does that look like?
Y.
A Y, and if we look at the old one,
Opposite.
it's an upside down Y. Okay, so it changes directions. Why? Because we did the ring flip. Okay. Now the next thing, let's color on our red and greens. Where are the red?
One is above and one is below.
Well, yeah, weren't they above and below last time?
They switched, so the one in the front is now below.
This is in front and still below. I don't understand. Yes, I'm being obtuse, but you need to push on this.
One in the back.
Green atom in back.
I don't know.
The red one is not up here.
Okay, up here and down here. So we're getting to that same words, but isn't that still above and below? Isn't it still above and below? Yes, but you're referencing, you're like, but it's not like just a little above and a little below, it's way above and way below. Okay? A rotation did happen, you're absolutely right. Okay? But if we look, there's red, and now where's our green? Oh, that was some lovely wording. I like that. Okay? We got that same slash through. Okay? And useful phrasing now is that the green atoms are now close to the plane. Okay? Where the red atoms were close to the plane before. We did the ring flip, and what happened? They exchanged their kind of relative distance to the plane, if you will. Okay? That relationship to that plane is now a different interaction and one we want to quantify. Okay? And one thing that we could do, which is what I believe you were getting at, in our top case, we could call those green atoms anti to each other. What would we call the red ones?
Gouge.
Cool. They would be gauche. What happened when we did the ring flip?
They switched.
They switched. The green atoms, whoops, as I start to write anti, are now gauche. And the red atoms are now anti. Okay. What does this mean for us? This means that there's a different aspect with those. Okay? A different relationship. How does that different relationship manifest for the overall molecule? Okay? We made it more complicated by having both the red and the green on there. So let's simplify it just a little bit. We're going to pull off the back. Or you guys like the front or the back?
Do it back.
You like the back?
Either one.
Okay. We're going to pull off the back. This is a Newman projection, right? And with Newman projections, we said that we could talk about, okay, staggered, eclipse, anti, and gauche to anything we wanted. Okay? So if I look at this green atom is gauche to this empty bond. Yeah?
Yes.
Why? Do I care? Why not? That's the way you said it, Mike.
They're not the same energy.
What is this empty socket up here?
I guess hydrogen.
It's a hydrogen. Okay? Is that ever really going to change? No, hydrogen is as small as it can get, which means that gauche interaction probably isn't a big deal. Okay? Because it's always going to be there. Okay? So what interaction could I see this green atom interacting with that isn't with a hydrogen?
Pushing each other.
What is it pushing against? And interestingly enough, it's not pushing against anything. The green one, I think, is actually probably the hardest. So let's switch it up and look at the red one. What is the red one pushing against? What carbon?
What is the pinky mean?
What's the pinky attached to? What is the red one pushing against? Could it be pushing against this carbon?
Is it pushing against the carbon it's bonded to?
Right? If it's pushing against the carbon it's bonded to, is that ever going to change?
No.
No. Unless the bond breaks, in which case we aren't looking at this molecule anymore, point of move.
So would it be then all the other carbons that it's not bonded?
Is it pushing against this carbon? Because it's not bonded to that carbon.
Just the ones that it's close to that it's not bonded to?
Do better. Where's my hand relative to the red atom?
It's behind it.
Do better. Yes, it's behind.
Across the plane? On the other side of the plane?
My hand's getting tired, so I'll just switch to a new hand. What's overlapping the red atom right now? My hand. Your hand is stupid, Mike. Okay, my hand's stupid. Let's let those atoms and my hand push away from each other to get more space. What happens? Did they get more space?
Yeah.
Ooh. What's that red atom pushing against?
The back carbon?
There it is, the back carbon. Because what's the relationship between the red atom and that back carbon?
Clips.
Nope. If there are clips, the bonds should overlap. The bonds aren't overlapping.
Parallel?
It's a Newman projection.
It's gauche.
It's gauche. I keep calling it gauche. It's gauche, isn't it? Whatever.
I think I don't know.
Way to mess with my pronunciation. You're right. Okay. It's gauche. Is gauche high energy or low energy?
Hi.
High energy. So what does it want to do?
Get
They
away.
rotate away from each other. When it rotates away from each other, now what's the relationship between the red atom and that same black atom? They're now anti. They're as far away from each other as possible. But now what's the black atom close to? Say it louder. Yeah.
The green atom.
Do you see it? The green atom is close. So what do those two do?
Push away from
They push away from each other. Now what's the relationship between the green atom and that back black atom? Ah, they're anti. So interesting. The structure is, whoa. I've never been able to pull that off. That was interesting. The structure is oscillating back and forth between these two chair flips, either alternating and bringing the red atom now. What's the relationship between the red atom and that black atom that I'm holding on to? Anti. Ooh, that's stable and good, but oh, green bad. So it rotates to get green to now be anti. But now the red is gauche.
So it just keeps going back and forth.
Ah. So what we're concerned about is that this position where the red atom is, or when we do the ring flip, where the green atom is, both of them are in a gauche unstable interaction. So what can you tell me about the green atom and where that red atom was? Where would you describe they were relative to the plane? Here's the plane. Where's the green atom?
Above the plane.
Above the plane. So it's only above the plane that matters?
No.
Because if we do the ring flip, what happens?
It's still above the plane.
Above the plane. But what happened to the other atom?
It's still below the plane.
It's further away. Or it,
So the red atom is now below the plane, but what about the green atom when I do that ring flip? Where does it start to hit? The plane. So what we're looking at in these two configurations is that our green atom in this top structure, okay, has the green atoms way above and below the plane. The red atoms are effectively in the plane. When we did the ring flip, what happened?
They swapped.
They swap. So every time we do a ring flip, we swap between being up and down from the plane versus in the plane. Right? We're using the word plane to describe both those orientations, and that could get nasty. Right? So what we want to do is use different terminology to reference those. Right? If we looked at this as, say, I don't know, there we go. There's my interpretation. You know, there's that. You know. Right? Does that look somewhat familiar to people? We made the rest of that blue. Did you say yes?
yeah,
Oh, awesome. What does that look like to you?
it looks like North America and South America.
Cool. It looks like the planet, right? Okay. And when we talk about through here, what are we talking about?
The equator.
The equator. So if we're looking at things on that axis of the plane, we'll call those equatorial. What do we call the top and the bottom? Okay, we can talk about them hemispheres, okay? But it spins right there, right? It spins about the axis. Guess what we call the ones that are up down? Axial. So we'll get axial references for things that are on the up down, and then we'll get equatorial for things that are on the plane. How do you spell plane? On? Okay. Why has that become important for us? It's because it's how we can now name and identify those positions. Because ultimately we said they're different, and what do we want to do to identify why they're different? We want to be able to name why they are different. Okay? So this green atom that we're looking at right now, officially what we're looking at is that bottom structure. Is that green atom axial or equatorial? Equatorial. Okay? What is its relationship to the atom I'm holding?
Same. You say that would be axial?
What is the relationship between those two atoms?
Anti?
That is an anti-relationship. Is the anti-relationship high or low energy?
No.
Low energy. Right? So we want our groups to be equatorial because it's lower in energy. If we now look at the red atom, what's the relationship there? To my hand. Gauche. Is that low energy or high energy?
Medium?
High energy. That's bad. Okay? So what the Newman projection allows us to go through and do is to define those two positions as high energy or low energy, and then also name them. So when we're talking about things that are gauche to the ring, those are high energy. That position happened to be known as, where is it? Relative to the plane. It's axial. So axial is a high energy state. Equatorial is a low energy state. So we would go through a ring flip. So we ring flip away, ring flip. Now what happens? That red atom that was high energy is now low energy because it's anti to the ring, which makes it equatorial. The green atom is now gauche to the ring, which makes it high energy, which makes it axial. Okay? All of those terminologies are things that we ultimately have to oscillate and deal with. So when we're talking about ring structures, one of the important things to note is where those groups are, because it drastically changes the overall energy of the molecule. How drastically? Okay? We've got a bunch of people that have studied some level of nutrition, right? Have you seen glucose structures? Yeah, glucose. Okay? In theory, I'm going to butcher the hell out of the glucose structure. But you might have seen glucose drawn something similar to this. As I, again, oh, you jerk. Sometimes the computer just flips out on me. Something like this, and we got an OH there, and we go OH. This look vaguely familiar to you? OH and OH. Kind of. Maybe you're used to seeing glucose drawn like this.
Yeah.
So is that a little better if we draw it that way? What is this structure right in the middle?
Your carbons.
It's not always the carbons. There's an oxygen there. Except ring. What kind of ring is it? It's close to a six-membered carbon ring, which means that ring structure, that overhead view that we're looking at, is inappropriate, and what we should be looking at is the chair configuration. Why is the chair configuration important? Because when we go through and look at glucose, we'll find that there's multiple forms of glucose. This is kind of neat. Okay? So from your backgrounds, where do you find glucose? Elaborate. And where would we find carbs and sugars? Why are we using carbs and sugars?
In our food.
What's the point of that food? Energy. Where else do you find glucose?
In your body.
Now you're getting real hyper-focused on humans. Don't talk about humans, talk about plants. Where do you find it in plants? Still in carbs and energy. Yeah, it's still energy. How do plants get their structure? What do they use?
Oh, that V, it's just the V?
Not that I'm aware of, but you could be right. I don't know enough about biology.
We have a
What do we
equation
make
to
paper out of?
glucose, fiber.
Trees.
What's in trees? Begins with a C.
Photosynthesis.
Carbon.
Cellulose. Guess what cellulose is? It's glucose. Does anybody see a problem with that? What is the point of cellulose?
Fat.
Cellulose? Not cellulite. Structure. Okay? We look at trees. Trees have this rigid structure because why? They have cellulose. But what is cellulose made of? Glucose. Where else have we seen glucose? In our diets. Okay? That gives us energy, allows us to live, which means we can break it down to get energy. Can we break down cellulose? That's a harder question. No, we actually can't. We do a trash job of it. This is why we don't do a good job of eating trees. Okay? Because we can't get the cellulose glucose out. What's the difference between cellulose glucose and glucose that we use for energy? This one is cellulose. You ready for glucose for energy? See if it'll let me do this nicely. This is the one used for energy. What's the difference?
Return from equatorial, that's
What turned?
the OH.
One bond went from equatorial to axial. That one bond takes us from a structure building molecule to I'm hungry and I need energy to live molecule. Single bond. That's flippin' wicked. And all it is the difference between equatorial and axial. You change the direction of that bond and the molecule goes from I can now live off of this to I can hit people with it. That's it. That's wicked. And it's all because of the different energy of those. What happens when you move into biochem? We have to name these. Which of these two do you think they discovered first?
The one in trees
If it's in trees,
or plants.
is it reactive? No. The whole point of it being in trees is that it does not react, which is why we can build blocks with it. This is why we don't build like walls with water, because water like free flows and changes shape and structure. Right? So what we'll get is that we'll find that you get alpha glucose
One beta
and beta glucose. What is the point of calling them alpha and beta?
to differentiate them.
It's just a numbering. Alpha was discovered first because it was reactive. They could study it. So they had glucose. And then they kept studying. Somebody in plant biology started studying cell structures and found that they still had glucose, but it was a different form of glucose. How do we differentiate them? You have to name them different. They're both glucose. So what do you call them? Glucose 1 and glucose 2. But with Greek letters, alpha and beta. That alpha and beta system, we will hear later on in the semester. We'll talk about alpha chemistry and beta chemistry. This isn't that chemistry. This is a completely arbitrary BS naming system. It's alpha and beta because that's the order that they were discovered in. That's it. That's absurd for a naming system. But that's how a lot of biochemistry is named. Okay? And all of it hinges back on what happens with chairs. That's amazing. You guys seem less impressed.
Did they know about chairs? Like, was that all established at that point?
No, I don't think so. I don't think chairs were existent at that point.
And then they were like.
Chairs
oh,
usually require
that's-
structure,
yeah.
and structure was pretty questionable at those discoveries. Yeah. If you consider atomic structure, what do we make up atoms with? Protons, neutrons, electrons. When did we know we had electrons?
I have no idea.
1900? I think officially like 1898. When did we know we had neutrons? 1940s, I believe, is when they actually confirmed that they existed. We theorized they existed for 30, 40 years and couldn't prove it. But it was the 1940s they figured it out. So when you talk about what we're drawing and representing, this is pretty freaking new stuff. We're talking almost within the last 100 years. Okay. Admittedly, my mind still thinks it's 2000, but 150 years, that's pretty crazy. We're talking about very, very new conversations, and we're constantly learning new things behind it. This is one of the reasons why biochemists have to be like, oh, well, crap. We have alpha glucose and beta glucose. We found two forms of glucose and didn't realize there were two forms, and they're vastly different chemistries. We have to come up with a way to differentiate that name. Okay? So So sometimes we have systemic names, sometimes we don't. Okay? But the point of this, why aren't you advancing? There it goes. The point of this is that what we're looking at is different energy states. We've got axial, which are crowded, and equatorial, which are open, lower energy. And if we think back to our individual states, axial sterically crowded, sterically is referencing electrons. Okay? So if we notice where you all sat, did you all sit at one table? No, because that's crowded. Okay? That's a high energy state. You don't be near people, you move away. Okay? That's our natural instinct. Electrons are effectively doing the same thing. Okay? So we want those groups to fill out as much as we possibly can. Okay? An individual molecule may be sterically crowded, and there's nothing it can do about it, but we have to acknowledge that it's a higher energy state. That's about it. So what we're trying to do is label those systems. Equatorial is now a lower energy state. Do we need Newman projections to define that? Yes. Do we need to always go back to Newman projections to reference it? No. As long as you know equatorial is the one that's more stable and how to draw it, and you know axial is the one that's less stable and how to draw it, that's all you need. You don't need to deal with the Newman projections, but the Newman projections answer the why those things are what they are. Okay, so what could we possibly do? You could encounter questions of what's the lowest energy conformer. Okay? We call them conformers because they're bond rotations. They aren't changing the identity of the molecule, but they're just rotations. So we could look at any one of these. Which one do you want to look at? We'll call it A, B, C, or D.
C.
C, there it is. We'll take a look at C. For the record, there were 4 things there, right? What would be a good thing to put on an exam? Nice and easy. Probably this exact question with looking at A, B, or D. Okay? Or maybe even just doing this exact question. Okay? So let's take a look. Cyclohexane. We've got structures already set up for us. We've got cyclohexanes. Okay? 6-membered rings. Okay? It says dimethyl, which means I need 2 methyl groups on it. It says position 1. A methyl there. And I can put a methyl, come on, pencil. A methyl there. Whoops, that would be 1, 2. Right? 1, 3. Everybody good with that? But now it says cis. What is that cis in reference to? Cis or trans. And when do we use cis or trans? Double bonds. Do we have a double bond? No. What is a double bond? It's a fun one. I have a carbon and a carbon. I have them bonded and I have them bonded, right? What is a carbon-carbon double bond?
Oh,
It's a 2-carbon ring. It's a nice way to reference it in my mind. Which means anytime you have a ring, guess what? You have cis and trans. So if we're going to call this cis, what we're saying is that these 2 methyl groups must be on the same side of the ring. The ring is effectively drawn as a planar structure, so how can we draw them so that they are on the same side of the ring?
flip it, or you spin it.
Does that make them on the same side? Okay. What is the hybridization of each of those carbons? Technically, all the carbons have the same hybridization here. But all we really care about is those red atoms.
SP3.
3, which means there's 4 groups of electrons. And if we have 4 groups of electrons, what shape do we have? A tetrahedron. And if we have a tetrahedron, can we have all 4 of those bonds all be in the plane of the molecule? Nope. 2 would have to be in the plane, 2 solids, and then we have to have 1 wedge and 1 dash.
Mhm.
If we've defined the ring as solids, what must the bond be to our methyl? Wedged or dashed? Take your pick. What do you want it to be? Cool, for the sake of time, we'll call it wedged. If that one's wedged, what must the other methyl be?
Dash.
Dashed, okay. Which means one of those is coming up, one of those is going down. Are they on the same side of the ring? No. And if they're on opposite sides, we would call that configuration trans. Is that what we're being asked to draw? No, which means they both have to be the same. Since I defined the top one as wedged, or really you in your silence defined the top one as wedged, the bottom one must also be wedged. If we defined the top one as dashed, then what must the bottom one be? Dashed. All right? How do we now convert this to a chair? All right, well, we have to come up with some kind of conversion process. For me, I would go through and number 1, 2, 3, 4. I would actually probably not number all the way out to 6. I would just go through 1, 2, 3. And an important thing to note is the direction we're moving. We're moving clockwise. Okay. I'm going to start this as carbon number 1. Where's my carbon number 2? Is it red or is it purple?
Purple.
Has to be purple to maintain that clockwise direction. 2, 3, 4, 5, 6. At position 1, what do I have?
Your
My methyl.
methyl.
Okay. Where's the methyl aimed?
Up.
Up. So where would I draw it in my drawing down below of the chair?
Kind of up. Oh.
I would draw it up. Okay. We move to position 3. What do I need to do? Put on another methyl. And where do I need to draw it?
Sun.
Up. Cool. Did I draw the lowest energy conformer?
Yes. Unknown.
Take a look at those methyl groups. Are those methyl groups labeled axial or equatorial?
It's the highest energy.
Okay. Annie's making a claim there that those are the axial positions. Those aren't the most stable positions. We would want them to be equatorial. How would we get them to be equatorial? A couple different options. Okay. The best answer in my mind is that you should go through and do a chair flip. If I sat in the chair that we're working on, where am I facing? Should be facing this way. This is my back. There's my feet. So you should be facing towards the left. Everybody see that? Let's take a look at the other chair over here. Where is it facing? Oh, conveniently, the exact opposite direction. So if we took that back, we'll call that a blue atom, and we're going to do a chair flip, what does it need to turn into?
Carbon. We count different.
Don't worry about that. If I take my back and I'm going to do a chair flip, what must happen to the back?
It goes down.
It goes down. The down atom in my new chair, conveniently already drawn, is right there. That feet atom, 4, is my new head. What happened to that axial position? Okay, it still must be aimed up, but when I do the chair flip, it changes from being axial to equatorial. The 3 position, if we count the same way around, still clockwise, 3 position, and I now need to put on my equatorial there. What is the relationship between those 2 chairs? They're the identical molecule, but they've done a chair flip. Why is it important to do the chair flip? Well, what was the question? Provide the lowest energy. Which of those 2 is the lower energy? The left one, because my groups are equatorial. So I have to be able to interconvert between all of these and to acknowledge how to represent those things. Okay? The axials should be relatively obvious, quote unquote. They're straight up or straight down. If we look at position 2, the axial is actually going to be straight down there. Position 6, it's straight down in the back over there. Position 5, straight up over there. Position 4, straight down over there. Those are all my axials, aimed relatively straight up and down from the plane of the chair. The equatorials, in our other position, get a little bit harder to interpret. Okay, whoops, I drew that one backwards. We'll understand why that is in a second. Okay, and those would be my equatorial positions. Equatorial are very challenging to define. So every time you have an equatorial position, if this challenges you, what should you also draw? The axial. Okay? Why is the axial at position 2 aimed up and not straight down?
Because it's the opposite of this one.
So there's not a bad idea, recognizing the pattern behind it. Okay? But if I delete that other one, how do you know it's aimed straight up? Okay? This is where it's helpful to actually understand rules on where you're supposed to be placing these and drawing these. By far, the axial are the easiest to go through and do. How do we go through and do it? Look at whatever position you're trying to evaluate. Let's evaluate position 3, okay, in my left structure. And I want to know where my axial should be aimed. Okay? Theoretically, we already know, right? Where should it be aimed? Okay? Here's our rules on how we figure it out. Look at that point of that carbon. Look at the ring structure bonds.
Oh,
Do you see a point of that? That kind of looks like almost an arrowhead. Where's that arrowhead pointing?
down,
Down. Where's the axial?
opposite.
Down. Because that's where it's pointing. Equatorial is not axial. So the equatorial will be to the side.
Oh,
Look at position 4. Where's the point aimed? More up or down?
up,
Which means where's the axial?
up,
Straight up. It's not numbered there, so let's go ahead and number it. Position 5. Where's the point?
down,
Go down,
Where's the axial?
down.
Straight down.
So that's only with axial.
That's only with
We're
axials.
ignoring-
Okay? So now I don't have to go, oh, it's axial because it's the opposite direction of the other one. I don't have to have the other one. All I have to do is look at the shape of my drawing. Which way is it pointing? The where that bond is pointing, or where those bonds are pointing, is the direction of my axial. Okay? What does that rely on? That you draw a darn good chair. If your chair drawing sucks, and that's usually the response that I get by that, is, oh, I don't know how to draw a chair, that makes it much harder to nuance and figure those things out. So you do the best you can. Okay? So how should you go through and draw chairs? Angle 2 lines, roughly the same length, but staggered off of each other. Everybody see how those 2 lines are staggered off? Look at the left half. Which line appears longer? Top or bottom? Which line appears shorter? The top. So I'm going to go up from the top position, and now I will connect. Look to the right half. Which line appears shorter? Bottom, which means I'm going to go down because it's on the bottom. Connect. There's a chair.
How do you know which way to draw it though?
Deciding which direction you want to draw it comes down to ultimately you. And if you don't want to draw it that direction, draw it the other way. How did we start this? We staggered 2 lines, sloped slightly to the right. Where was our chair facing? Our chair faces to the right. So if I want the chair to face to the left, what should I do? two lines, but now sloped the other direction. Again, split it in half. Half kind of weighted. Which side do you want to look at first, left or right? The right half? Which line is shorter, top or bottom? Say again. Which line is shorter, top or bottom, on the right half of that drawing? The top, which means go up, connect. Look to the left half. Which line is shorter, top or bottom? Which means go down, connect. If I sat in that chair, where am I facing? That way versus that way. How do you decide which one you want? That depends on the question that's asked. Okay, kind of, sort of?
So for the trick for the axial, is that like, it would be something like draw this chair with axial whatever? Like how would you know to draw axial versus?
How did we know to draw our cis 1-3 axial versus equatorial? How did we do it?
I don't remember.
Okay, can I backtrack? Will you let me do this? First, what we did is drew the overhead. The overhead was theoretically more straightforward to see, the 1-3 cis both being up. We then drew a chair. Didn't matter what chair at that point, because all we're being asked is whatever's lowest energy. Okay. We then picked where we wanted to put our methyl. For me, I picked the 1, or in this drawing, the 4, either of those two positions, because those are the extreme cases. Doing anything on the seat can be more difficult to do. So I start with 1 or 3. Okay, so I picked my 1. I drew that methyl where? Up. Where's up in this chair? So there I drew my CH3. That might immediately set off alarm bells, because if I'm paying attention, that CH3 aimed up is axial. And what did I want? Lowest energy, which means I already know I'm drawing it wrong.
So you just picked to do up and then you just have to go
Yep.
through the motions. Okay.
Okay.
There's no way to just like, you're not, I mean, you probably know already when you're going through, but.
There is no up, there is no down, there's
Yeah.
no left or right.
Okay.
Okay. So what you could have just as easily have done is said that these were dashes. In which case, if I go to position 1, where's the down direction from position 1? Can I do this? Is that a valid way to draw it, that black line?
No,
No, why not?
because that's still technically axial.
Nope, it's actually not axial. Okay? It's not axial, similar to this shape right here is a star. That's not a star. Exactly! You didn't draw an axial. Okay? Did you draw equatorial? No, you just drew a line wherever the hell you felt like it. You can't do that. There has to be a reason for it. Okay? And if you don't know where those positions are, that's okay. That's where that understanding needs to come into play. Okay? Where's the point? Where's the point at position 1? It's aimed up. Okay? So if I draw straight up, that's axial. What did I want?
Lowest energy. Oh, dashes.
I wanted it down, which means I don't want to go straight up. I want to go equatorial. The equatorial, where the equatorial drawn? Not axial, so try and get them off the up-down axis. And then the next bet, parallel to the second bond away. This is a first bond, this is the second bond. See how this and this are parallel? Where's that arrow pointed?
Technically down.
There it is. That's why it's down. This is why the equatorials are very challenging to nuance, because you get ups and downs that are very subtle, particularly heavily dependent on your drawings. This is why drawing them axial becomes much more relevant. You nail the axials, the equatorials are the opposite directions. Kind of, sorta? Officially, we got 4 more minutes. To this official, what we'll talk through is some of this kind of chirality stuff. Okay, and we'll pick up with chirality again after the exam. What chirality is referencing is an atom, in this case this carbon, that is connected to 4 distinguishable things. We're connected to a nitrogen, we're connected to a carbon, and an implied hydrogen. Are those atoms distinguishable?
Yes.
How is carbon distinguishable from carbon?
They have different bonds.
That carbon is connected to a carbonyl. I can tell a difference between those carbonyls. Where is that difference? I hope really freaking close, but it could be 30 carbons down a chain before you find the difference. You track all the way back to where it branched, that's a chiral atom. Why does this become incredibly important? This particular drug became super relevant in the 1950s. It's known as thalidomide. Thalidomide effectively cured morning sickness. Okay? So if you've ever heard pregnant women complain about morning sickness, this drug cured it. Okay? Didn't have to worry about morning sickness at all.
Didn't they have deformities and stuff?
Yes.
Yeah.
And so what ended up happening, okay, is however many months later, because I don't know when morning sickness sets in and all of that, okay, they would give birth and they would notice that the babies that were born had massive deformities, all sorts of limb deformities. And they tracked it back to this drug, sort of. This drug has a chiral atom. And what's happening at that chiral atom is that we're supposed to have 2 solids and a wedge and a dash, because there's 4 groups. So there's our 2 solids, there's a wedge, and there's a dash. Okay? Or, whoops, it could have been a dash and a wedge. Remember how I talked about glucose? It's just which way the OH is aimed changes drastically the end result. Where that hydrogen is aimed, be it up or down, drastically changes the outcome. They didn't think it mattered. So they gave people the drug with both of these forms. One of those forms did a phenomenal job of curing morning sickness. The other form decomposed into the body and turned into a massive mutagen. And that mutagen caused all sorts of side effects within babies. All it came down to is a carbon with where the hydrogen is aimed. Wicked small difference turns into a drastically huge, massive change in functionality. So it becomes really, really, really important to evaluate and understand and name and label and all of that fun stuff. Okay? When we go through and talk about that, what you're referencing at its purest is that chiral means non-superimposable on its mirror image. So if I take my right hand and I put a mirror here, what would project over here?
Essentially, what would look like left hand?
Boom, there we go. Are those hands non-superimposable?
Yes.
Okay, and this is where some people go, aren't they superimposable? Aren't they perfectly overlapping? They're not perfectly overlapping because what I'm overlapping is the top of my right hand with the bottom of my left hand. Those aren't superimposable. My hands are chiral. How important is this? No one's left-handed. Did we already ask that question? Talk to your left-handed friends. They will talk about how important it is to have chirality because they'll always complain about left-handed scissors, or rather, the lack thereof. Scissors are designed for right-handed people, and if you try to put right-handed scissors into your left hand, it hurts because it's not fit, because your hands are chiral and scissors are also chiral. The drug is effectively scissors when it comes to your body. Your entire biological system is built up of molecules that have one particular handedness. Since they have that one-handedness, your body will respond to molecules that have different handedness differently. Here, no sickness versus, what's an appropriate word? I already forgot. Deformities. Okay? Other cases, you can smell carbone. Carbone as a chemical has two different forms. One of them smells like mint, one of them smells like caraway seeds. All it is the change in the direction of a hydrogen. So it turns into a massive, massive difference. Your biggest definition is it's superimposable on its mirror image. Okay? That's not particularly relevant because then what you would have to do is draw mirror images for all your structures. So instead what we kind of push is we look for a chiral center, a carbon with 4 distinguishable groups. If you have that carbon, you now have the potential for chirality. That chirality could turn into the difference between mutations or not. Okay? Why is that important? You remember that diagram, this thing. See that stereoisomer category? That explodes. And you now have to evaluate mirror images and you fall into these extra 2 categories. Is that a pain to deal with? Yeah. 1 question at most. Okay? 1 question at most on the exam.
Of what?
Of being able to differentiate enantiomers versus diastereomers. So getting all the way through that. You compare 2 structures. What makes it extra challenging? Spin, flips, sigma bond rotations, all of that fun stuff.
Wait, but what's the, is it like chiral is chiral?
If you have a chiral atom, if you have 4 atoms,
Yeah.
4 unique atoms that are connected, yes, you have to evaluate the 2 structures. Are they mirror images? If
Oh,
they're mirror
images.
images, then the
And
relationship
we
is
can't use
enantiomers.
this on the test?
He said no.
I'll add it.
I know.
I'll add it. I'll add it.
You have?
I'll add it.
Oh, that's.
What if you just add the bottom part?
I can. It's not that. That's probably harder to add the bottom part than to add the whole flipping thing. I'll put the whole thing on there, and then I will remove RNS. To be honest, I don't think RNS is actually on there. E and Z are the same thing as RNS, same rules, just applied differently. When we talked about E and Z is around double bonds, RNS is now looking around a chiral atom. Very, very particular, very, very spatial oriented. Same rule set, but more complicated to deal with, so we won't worry about RNS on the exam. I at least wanted it up there so you can kind of see what's going on with it. It's looking at a particular molecule in a particular configuration. Okay? So things that I need to go through and do, if I have RNS on the exam, I need to remove it. And then I need to get this into the exam. Okay? Questions before I end it? I know, ending it late.
How many minutes do we have?
Class 75. 75 minutes, and you're looking total ballpark 40 questions. It's probably a little under 40.